Waterloo from the Institute. He should be pretty familiar to at least some fraction of people here. So Avery started off his career as an astrophysicist at Caltech. Did his PhD work with Roger Blanford, radiation transfer in the vicinity of black holes. I remember Avery got the inaugural Theoretical and Astrophysics in Southern California award talk for best talk, and all this other grad students from places like Santa Barbara were very jealous at the time. So he followed.
Did you find out how much it was worth?
Yeah, then we found out how much they actually got for the work. But so that's when I first met him. So he followed that up with a postdoc at the CFA. He was an ITC fellow. And then, of course, after the ITC, he came here where he was a senior research associate. And for about, I guess, 2 years, a little over 2 years now, he's been an assistant faculty at Waterloo and worked at the Perimeter Institute. And so today he's going to tell us about some work that actually started here at CITA with some fellow citizens, Christoph and Phil.
Thank you very much, Shane. So when I was hired, I was a black hole astrophysicist, and I did my darndest to turn into a cosmologist immediately thereafter. But this is my story about how black holes, supermassive black holes, might be playing a role in the cosmology of the low-density universe that is qualitatively different from what people have talked about before. And I want to highlight non-local, sort of a non-local AGN feedback, and I'll mention some of those consequences. I'll explain what that means. It's a slightly different non-local than you might run into most times at Perimeter. So just to highlight what Shane said, this all has a strong connection to CITA. So I'm sorry you're tarred. You're not going to escape. Three of us, Phil, Christoph, and myself, all started doing this while we were here. And now the diaspora has spread, and we've enmeshed a few other people, including Wolfers Spring. All right. So just to give you an idea of where we're heading up front, I'm going to first tell you a little bit about the extragalactic TeV universe, so set the stage. I'm going to introduce a modest hypothesis. So I'm going to try my best to convince you that plasma instabilities are really important in cosmological contexts. But if you don't believe me at the end, and you should rightly be suspicious, consider that hypothesis. Because then I'm going to try to show you a number of consequences, a number of which have already come to pass, some of which might give you pause about other plane measurements. And I'm really going to try to hit the ones in the bracket. We probably won't get to these guys down there, but if we do, that would be great. The take-home message is exactly what I said at the beginning. The luminous TeV sources, so very high energy gamma ray sources, might be playing a critical role in the low density universe. Somewhat counterintuitive. All right, the TeV sky. So the TeV sky is measured with air Cherenkov telescopes. You basically stare at the atmosphere, you wait for a cascade from either a cosmic ray or induced in this case by high energy gamma rays, and you watch the Cherenkov light in the atmosphere. So it's sort of like super Tamiya in the atmosphere. And when you do that, there are a number of dots on this projection of the sky indicating known TeV sources. Many of them are really cool things like supernova remnants. You can see the sites of particle acceleration, etc. That's not what our story is today. We're really interested only in these extragalactic sources. So a handful of the sources in the previous plot, and by and large, they all look pretty boring. They're all unresolved point sources. Here's Markarian 421, one of the brightest. And they have relatively uninteresting spectra. Most often fit fairly well by a power law. So this is Markarian 421 on a number of different days. Each symbol type is 1 day and one observation method, or one observation observing telescope. And so it varies by about an order of magnitude, but it has this power law shape. And as of today, there are around 30 or so, maybe 40 sources for which spectra are measured. So there's no quiz later. I don't expect you to memorize the picture. Only note there are about 30 lines. Okay? And that brings me to cousins. So in a remarkable instance of bias, we of course carve up the optical spectra by tiny fractions of a decade, and the gamma ray spectra from 1 MeV up to infinity is all gamma rays. But they're not all the same. These guys are all TeV sources. But we have this wonderful telescope, Fermi, that's observing stuff up to a few hundred GeV. So an order of magnitude less. All right? But nevertheless, unlike this situation where we have roughly 30 sources, Fermi is doing all-sky surveys, and so there are thousands of sources, extragalactic sources that Fermi sees. And that means you can start doing things like segregating those sources into populations. So extragalactic sources from Fermi look like they come in two forms: flat spectrum radio quasars, which we're not going to be very interested in, and BL-lac objects. Okay. I'll say something about the x-axis in a moment. And these two different populations do have very different properties. One that would be important to us is the photon spectral index. So this is a lot like the spectral index. I always keep the photon there because I get confused. The NDE goes as this, and OE to this power. But yeah, they look characteristically different. They have different characteristic spectra. They're not amongst the individual objects in BL-lac class. They are subcategorized by the shape of their spectrum in the Fermi band, which is directly related to the location of the synchrotron peak in the spectrum. So this is a characteristic spectrum for one of these BL-lac objects. You have a synchrotron peak, and then you have a Comptonized bump. And Fermi sees the Comptonized bump. And if the synchrotron peak is at low frequencies, the Comptonized bump, the thing that Fermi sees, is steeply declining. If it has a synchrotron peak at high frequencies, the Comptonized bump can be increasing.
So this is synchrotron self-Compton?
Well, it's synchrotron plus Compton. It's probably not synchrotron self-Compton in a single population. My story, since Fermi is an order of magnitude below the energies we're interested in, is really going to be focused only on things that are rising where Fermi sees them, so presumably bright in TeV. Okay, we're going to throw away these guys. There are a number of correlations between the properties of those guys and the TeV fluxes. Typically, as that synchrotron peak, that was the x-axis in that other plot, that synchrotron peak moves to higher and higher frequencies. Okay, the TeV brightness goes up. That's not surprising. As we move to higher and higher luminosities, TeV luminosities, it also gets harder and harder. The spectral index goes down. Both of those are not terribly surprising. Oh, and you can tell that I'm becoming Canadian. I put a U in my papers. All right, so these BL-lac objects, even though they're subcategorized, they don't really fall into discrete categories. There's thought to be, even all the way to that other class of objects, those FSRQs, a continuum of source properties. Okay, just moving that synchrotron peak moves the location of the Compton peak, and it becomes harder and more dominant in high energies. Okay, so just to say, it's all one big happy family. And again, we're interested in these things. All right. So if I remove a handful of kind of weird sources from my list of 30 TeV bright sources, all the rest of them are this blue-like thing, this HSP, these high synchrotron peak sources, these hardest of Fermi sources. So already Fermi tells us something about the source population. But the interesting thing I think in this plot, and I know you've all been, or this table, and I know you've been inspecting it carefully, is this column here is the redshifts. They're all actually quite low. If you were to histogram them up, they all fall off right around 0.2. That's sort of surprising. I mean, there's no good reason why Fermi can't see things out past Z of 0.2. The answer to why all of these objects appear to be very close by is that they're absorbed at TeV energies. And so in a highly schematic way, the way that that occurs, we have our blazar over here, our knitting needle model of AGN. It's a blazar, so it's pointing the jet at us. All of these BL-lac objects are blazars. There we are. The blazar is emitting TeV photons. It's one of these TeV bright objects. And those TeV photons are not propagating through an empty universe. The universe is filled with, amongst other things, an infrared background, an extragalactic background like from stars. And when one of these TeV photons meets one of these infrared background photons, they lie above the pair creation threshold, and it generates an electron-positron pair. Now, this doesn't happen near the source. This happens at cosmological scales. Typical numbers at Z of 1 would be 35 physical megaparsecs. Okay, so twice that in co-moving megaparsecs. Today, because there are fewer extragalactic background light photons, it's almost an order of magnitude higher, almost a gigaparsec. Okay, so these are cosmological scales over which this happens. If you calculate the optical depth of this process, as seen from Earth, so how far away you could put a source before you drop its flux by E, you get some surface in redshift and energy. The interesting thing is just to point out that it's about 1 at Z of around 0.2. Right? So this really does quantitatively explain why there are so few objects. In fact, Fermi sees the effect of this absorption on the spectrum of gamma ray objects. Right? Fermi sees things quite further away, since it's looking at lower energies. But it sees the effect of this at low redshifts. There's almost no effect on the spectrum, and as you go to high redshifts, there's a break that moves down in energy, so corresponding to moving to higher and higher optical depths of direction. It's also seen in attempts to measure the extragalactic background light distribution. So here's a picture of the tau equals 1 surface as a function of energy and redshift. Okay, so this part isn't controversial. The TeV photons are absorbed. And that's why there's no sources beyond 0.2. This talks really about what happens next. We have this population of pairs. They're moving very, very rapidly. And again, they're not propagating through vacuum. Okay, so the universe they're propagating through still has this extragalactic background light, but it also has CMB photons. And if one were to hit a CMB photon, it would Compton upscatter it, because the CMB photons are about 1,000th as energetic as the infrared photons. You get GeV photons out of this process. So one TeV photon will produce a cascade of these GeV photons. Of course, it could hit another one of these infrared background photons, pair create again, and produce a cascade. Both of these processes have the effect of reprocessing the original spectrum, okay, which is presumably something like power law, down to lower energies. It eats up this high energy tail and drops that off in low energies. But we're thinking about maybe something different happening. And the reason why is this isn't only happening once. We don't just make one pair. There are pairs being made throughout space, all from this one set of gamma rays. And these pairs are moving very, very fast. Lorentz factors typically of about 1 million. That's what you get when you take a TeV photon and an EV background photon and let them into each other. And they're also highly collimated. They're moving within the same direction to an angle of 1 over gamma. So 1 millionth of a radian. And they're moving through something that's ionized, an ionized background intergalactic medium. And so this is why fusion is so hard to produce. It's plasma instabilities. And so we're suggesting maybe that paraplasma beam instabilities are what eat up the energy from these beams. So we don't reprocess them to lower energies. They get dumped into collective motions. Now, let me be absolutely upfront about isn't plasma a little ambitious? What's the typical density of our paraplasma? I mean, we have to do all of these things that only are done over gigaparsec scales. What is the typical density? Well, it's something like the energy flux times how many particles are being produced locally times a 1 over production rate, okay, or times a time scale over which particles are cooling. So flux, how many we're producing per length scale, a cooling time scale. Typical cooling time scale you might plug in as an absolute minimum would be, or absolute maximum, so cooling rate as a minimum, would be that from inverse Compton. So we know if nothing else happens, those energetic pairs are going to cool by inverse Compton. That happens, you plug in those numbers, you get some redshift dependence, some luminosity, etc. But here's the real number to look at. Typical densities of 10 to the minus 22 cubic centimeters. So even for cosmologists, that's an exceedingly small number. A plasma scale associated with that, if we just took this and naively stuck it in and computed what the plasma skid depth is, that'd be about a nanoparsec. And the condition that we are a plasma is that we have many, many particles within this plasma scale. Oh, I'm sorry, we take the IGF, it's a nanoparsec, right. So the condition that we have a plasma is that we have many, many beam particles, many of these guys, within this nanoparsec plasma scale in the IGF. Okay. And that puts a constraint upon this d tau dl, which we think we know, so therefore this flux, and thus the luminosity of the sources. So dim enough sources won't produce enough pairs to be interacting collectively with the intergalactic medium. Our sources, however, all lie above the luminosity threshold. So all of these dots are the points in that, or the sources in those tables, for that table. And these lines here show, for different assumptions about the cooling, where the limiting luminosity is. Points above this line should be bright enough to produce pairs that will interact collectively with the IgM, even with such tiny densities. Okay. So how do they interact? So I have two schematic ways to describe it. So the first is the two-stream instabilities. This is something that you may have come across in your undergrad plasma physics class. It's a one-dimensional picture. It just has longitudinal electrostatic waves. So these are Langmuir waves. They're like sound waves. Just charge density fluctuations in space and a corresponding fluctuation in electric potential. They oscillate at the plasma frequency. Sound waves. Okay? And if I have two components, an IgM or a beam, and I look at the leftward propagating mode in the intergalactic medium and the rightward propagating mode in my beam, and we have a small velocity, there's very little difference. Okay? But as I start to increase the velocity of the beam, this is still moving backwards in the frame of the beam, but the beam's moving by so fast it looks like it's stationary. And if we increase it enough, it starts to move with the IGF. And now we can get resonant energy transfer. And that's all the two-stream instability is. It's the coupling of forward propagating modes in the intergalactic medium with backwards propagating modes in the beam that are being dragged forward by the beam's motion. Okay? So this produces resonant energy transfer. That's the instability. You can convince yourself that the energy in those beams are negative. It's very much like the Kelvin-Helmholtz instability, why there are waves on the ocean, unstable energy transfer. So that's the classic two-stream instability. Typical time scale for that is 1,000 times, the rate's 1,000 times higher than inverse Compton for the beam densities and Lorentz factors we've got. Okay, so quite high. Much shorter time scale. That was when we had everything parallel. You could also think about the other limiting case where everything's perpendicular. That just gives you the Weibel instability. And so if you think about high energy events like gamma ray bursts or shock waves around supernova, this is frequently invoked to explain magnetization. It's a very similar situation, except now we have an electromagnetic mode. It's propagating across the beam, so particles are flying in here. We have fluctuations in the magnetic field. Particles are deflected by the magnetic field. They concentrate into filaments, which enhance the magnetic field instability. Okay? The Weibel instability growth rate also can be written down in terms of a density ratio, Lorentz factor. And again, it's quite large. But these are really just two limits of a more generic instability. Okay? One where we're longitudinal, the other where we're orthogonal, but of an oblique instability. One where we could have the wave vector of the excited modes off in some random direction. There's a maximum, and at that maximum, the growth rate is actually quite a bit higher for relativistic plasmas than the two-stream, which itself was much higher than the cooling rate, the inverse Compton. Does this actually all work? Well, first let me just say that in principle it does. People do simulations of this. They see filamentation. They see the development of structure in the beam. And it grows at the right rate to be associated with this oblique instability. Okay. But there are some complications to worry about. Well, the first is, I just talked about one sign of charge, but there are two signs. We have pairs, not just electrons and not just positrons. It turns out that makes no difference. Everything still works. A more severe problem is the difference between cold and warm beams. So the stories I told you were all for plasmas where they only moved as a consequence of the electromagnetic forcing. Okay? So that meant if they executed some cycle, while the wave amplitude grew, they always contributed in the same phase of the wave. But if we had a hot beam, a beam where thermal diffusion across one wavelength was large, you might get enhancement and then decrement. Okay, so you have to worry about that a little bit. There's a natural way to do that. What's warm depends upon the details of your instability, the direction of the velocity dispersion you can deal with, etc. Suffice to say, that's something that you can think of. In any case, there's a kinetic growth rate that you get once you worry about these warm beams. It's a little bit less than the maximum that you got for the oblique mode, but it's still plenty high. Okay? And finally, self-consistent beam densities. If these beams are cooling themselves by plasma instabilities, the energy in these beams are going away because of collective motions, we have to put that in when we calculate the beam density. Of course, we have to be self-consistent. The big complication, though, those we can handle, is nonlinear saturation. Okay, so where those simulations have been done, the waves saturated order unity amplitude. So they dump large amounts of energy into the rate of motions. However, it's not clear that you can't suppress the growth of these via nonlinear effects. Okay, and there's, for example, limits for particle wave scattering would seem to imply that we have roughly a tenth of the growth rate that I wrote down before, and I'm going to assume in a moment. But these things are serious questions. Okay? So even though we have nice pictures like this for the nonlinear saturation in a rather inapplicable regime, let's just be upfront and say we don't know how it's going to saturate in our extremely large velocity, very large Lorentz factor, extremely large density concentration. However, what if we assume that they grow roughly at the linear rate? What does that mean? Well, I can draw a picture kind of like this, which shows cooling rate as a function of energy for the incoming gamma rays, or equivalently Lorentz factor for the paired beam. Okay. Here's where inverse Compton lies in this, just standard inverse Compton cooling rate. There's where the two-stream was. There's the Weibull instability. There's our oblique instability. And this whole region up here is where we would cool so fast that the plasma story wouldn't hold at all. There'd be no plasma because there'd be too few particles, too low density. Of course, if we're up here, then I think that collective phenomena have already won. Okay, so there's the oblique instability. You can do this at a number of different redshifts. Again, inverse Compton and oblique, the two ones that matter. And for a large range in energies, for these very high energy gamma rays, it looks like the plasma instability cooling rate up to Z of 3, almost Z of 6, dominates inverse Compton cooling. So the story of those pairs is written by plasma physics, not by inverse Compton, as long as we adopt that linear cooling rate, linear growth rate for cooling rate. Okay. So you can think of that as an interesting result. Plasma physics might be important. Cosmologists had better crack open their plasma physics textbooks. Or you could think of it as a modest hypothesis. What if that is true? What does that mean? Okay. And I'm reminded of a quote from Mark Twain. I like Mark Twain a lot. I didn't like this quote so much when I first saw it. There's something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact. It sounds like it applies to some people I know, but I'm going to turn it around. I think that one gets wholesale returns of understanding out of such a trifling investment of conjecture. If we assume this, we're going to be able to solve a few problems. So the first is the intergalactic magnetic field. So how does this relate? So here are three different TeV sources. And those three different TeV sources, here's the TeV data. Okay. They're fit by some model, the TeV data. And that process that we talked about before, inverse Compton cooling, reprocesses energy or emission from high energies down to low energies and produces this cascade bump. So this dashed line is the intrinsic emission, And this bump is the cascade emission, reprocessed emission that was eaten away by absorption on the EVL. Okay, so that's intrinsic, there's the cascade. And here's Fermi's limit on what the flux is in the Fermi band, okay, around GeV to 100 eV. And you'll notice it eats right into that cascade. And this is not quite the worst, but one of the worst cases. This one's a little worse, that one's a little bit better. The cascade just doesn't look like it's present. So why not? You know, this is sort of like the dog that didn't bark. Where did it go? The story that many people have been telling for a number of years now is that this must mean that there is a strong intergalactic magnetic field. And the way that that comes about is we have our TeV photon originally, it produces our pair, and remember we said we saw a cascade of GeV photons as those pairs Compton cooled, but what if there was a strong field, then these pairs would deflect. And they would send that GeV emission off to somebody down here. We wouldn't see it. We would certainly see GeV emission from sources we didn't see as TeV sources, but we wouldn't see the TeV emission and the GeV emission at the same time. Now that requires a strong enough field to deflect it enough to account for the width of the beam, or the width of the jet. Okay? And from that you get a limit on the magnetic field depending upon how pessimistic you are, up to 10 to the minus 15 Gauss. And that's an exceedingly interesting number because with contraction and a couple windings, that produces a galactic field with a nano Tesla. I'm teaching a class on stellar astrophysics, and I've got all of these SI units in my head. Microgas, 10 microgas, 10 microgas field for the galaxy. Okay? So that can produce galactic field without any difficulty, if that were true. But as I like to point out to people, must is in fact a four-letter word. It's one we should probably not use for science. And the reason is, as soon as we add another mechanism, like plasma instabilities, this whole argument goes away. As soon as this is viable, then this doesn't necessarily imply that it's an intergalactic magnetic field. So I'm a little bit pessimistic at the present moment that the limits we see tell us anything about the intergalactic magnetic field. In fact, how much energy could be coming out with inverse Compton? That depends upon how far away the objects are, but less than 10% of what people would have guessed, and even worse than that, in fact, because as soon as we have these plasma instabilities saturating, we would expect to isotropize that distribution. So you don't need the magnetic field a priori to deflect them. The magnetic field's produced in the instability itself. So you could drop this by another 2 orders of magnitude just from gas ionization. So that's one thing. The second, and the subject of a lot of our recent work, is the implications for the luminosity function of the special subset of objects that are TeV bright. TeV Blazar luminosity function. So we can measure this today if you allow me to make a number of assumptions. Okay, so first, let me assume that what Fermi sees as particularly hard gamma ray blazars is the same population as my TeV blazars. Remember, Fermi has done an all-sky survey. These TeV blazars are measured only by pointed observations. They only look where they think they should look. Let me also assume that all the TeV observations, despite coming from a large number of different telescopes, have similar flux limits. This is sort of the competition assumption. Assume that everybody competes until they're competitive.
Hang on one second. Did you count the number, density, volume density of the objects? Are they similar? The TeV blazer, hard gamma blazer.
I'm gonna normalize it by similar. I'm gonna normalize it in similar regions. So I'm gonna look out to see a point two. We can't count the number density because we don't actually have an all-sky TeV survey for the TeV blazars. They're all pointed. So we look at M87 because it's interesting. Is that not what you're asking?
Well, so even if it's pointed, you can still say what. Okay, so you have no estimate for the volume you could have seen this thing at.
Yeah. I mean, I think I can see out to Z at point two, as long as it's, you know, that's the absorption limit. That's I think much more significant than the flux limit.
But so I guess that's the question. How are you finding TeV blazars? You're looking at known AGN, or you're just trying to do an all-sky survey with these?
I am going to ignore all of the biases in the TeV sample, which is strongly biased by target selection, by scheduling, and other stuff. So I'm just going to take this table, I'm going to plot it up, and I'm going to say mea culpa and LISM. What do we get?
So then you're not necessarily just assuming things. That's what I'm saying. I'm trying to.
I'm not assuming that I'm not assuming that the luminosity function is the same. I'm just using this to account for static curvature. And this is what you get. Modulo all of these things that Norm had just mentioned. These dots right here. Okay, so it's a few bins. That's nice. They really all have a similar flux limit, but you can ignore that. We got a few points. We have what looks almost like a double power law, as much as you can do from 5 points. The really interesting thing is this dashed line, it's a fit of sorts, but it's not a fit to a double power law. This dashed line is actually the quasar luminosity function at z of 0.1, just shifted down. So if you take the quasar population within the region that these TeV Blazars exist, and you just shift down in total number, and you shift over a little bit in luminosity, you renormalize luminosity, you actually fit the objects that are seen. Now maybe that's because they looked at quasars, but they didn't. They looked at blazars. So put another way, there's just a rescaling between the quasar luminosity function, this phi q thing, and the blazar luminosity function, this phi q thing. Now why would that be? So one picture in which you can imagine this is that both the quasars and these TeV Blazars are regulated by the same mechanisms. They're both accretion-driven events. They're regulated by how much accretion you can have into your halo, accretion on your AGN. Another way to say this, and the second thing is like contemporaneous parts of a single AGN population. Another way you can say both of these is they're really just different accretion states of the same kind of object. And those accretion states exist contemporaneously. Okay, so if you wait long enough, you see X-ray binaries move through different states. If we wait long enough, we'll see each AGN move through multiple states. And this immediately raises the question, were these related in the past? That is to say, can I take out that 0.1 and replace it by a function of redshift? Now, if you want to do that, there are a number of things you've got to worry about. So the first is the spectrum of these sources. Because as soon as we start redshifting them, that spectrum is going to move, and it's going to be observed. It's going to be absorbed. So we lose the high energy tail. And that is to say, it's going to depend upon what this low energy bit is. All right, there are 3 different colored lines here corresponding to the same intrinsic high energy spectrum, but there's a break in the different low energy spectrum. So I need to know something about the distribution of those. So I'm going to appropriately k-correct my TeV sample and try to reconstruct something there. I can estimate what the distribution of this is just from very nearby sources. So we can just look at the Fermi sources, or the Fermi spectral indices, the low energy spectral index specifically, for the sources in that table. If you do that, they're roughly Gaussian. The blue lines are roughly Gaussian. Okay? They're not too different from the Fermi Blazars. And they're hard, just like we said. Okay? So that means that we can construct not just luminosity function in redshift luminosity, but one in redshift luminosity and spectral shape. And it just has this measured spectral shape. You assume that that's fixed. The second is absorption. You have to worry about the fact that as we go to further larger and larger redshifts, this high energy bit gets absorbed. And so the spectral index that Fermi will see, so for example, for this amber line, will look quite a bit softer. So you'll be misidentifying sources. Here's a picture of the spectral contours of spectral index as a function of redshift for this absorbed double power law model for a given low energy spectral index, low energy spectral slope. And the blue points, which are the Blazars we're after, more or less follow this. Okay. The nice thing about this is at the end of the day, I waved my hands a couple times to tell you we have a model, but it really ends up being a zero parameter model. We fit what we think the spectral index, the spectral distribution is. We have the quasar luminosity function, so we know what this thing is. You know, we have an ansatz that the two are related in a simple way. We have no parameters. Surely we can falsify that, especially because the number of sources increases dramatically in the past. I mean, right now, everything is turning off, but if you go back to Z of a couple, there are many orders of magnitude larger co-moving volume. quasars out there, and therefore by inference, these TeV Blazars. There are two places we're going to try to probe this. One is by looking at the statistics of the sources that Fermi sees. So this is going to probe stuff close by. And another is to look at the gamma ray background. The light that's left over after you've subtracted out everything you know is producing gamma rays in the extragalactic universe. And that's going to probe high redshift. And there are two ways to do this Fermi statistics business, to study this low redshift part. Two easy ways. One is to look at the redshift distribution of objects, and the other is the flux distribution. Really, these are just different projections of our luminosity function. Okay, they have different limits in integrals. Okay, one goes over all redshift, one goes up to, I'm sorry, all redshift goes up to some limit. They both have the detector response of Fermi plugged in some way. The fact that Fermi has a hard time seeing things further and further away, etc. Okay? But really just projections. Okay? So you got to be a little bit careful. How do we do with the redshift distribution? Well, the blue points are the latest ones. And if anything, it looks like we underpredict the high redshift number densities. That is, even with our rapidly evolving, or rapidly increasing population of TeV Blazars, we don't quite get enough, at least according to Fermi. How do we do with the flux distribution? This is the first Fermi hard object catalog. All right, so they took everything that had detected fluxes. I think it's above 10 GeV, but detected fluxes above some number, and they went and made a catalog out of those. These are presumably all of our hard objects. And remember, we're looking at things that have energy at highest energies, have flux at highest energies. The gray bit is the data. This blue line is the one you should look at. This is our estimate for the flux distribution. Okay, and down here, this is just some fluctuation. This gray bit's the 2 sigma variations about that. This is just some flux distribution, Poisson fluctuation about this relative to this blue line. We certainly get the slope and the magnitude exactly right. No parameters. There's no dial we turn. Okay, so at low redshift, I think we do just fine. So that's good. The next is the extragalactic gamma ray background. So this is where the state of things were as of 2010. There was 2 measurements of the extragalactic background by egret. Fermi came along and added these points here. This is really the limit that we're going to be looking at. That's interesting because if you take typical models for how many blazars there can be, the cascade emission pushes you over this Fermi limit. That's what the gray band is here. So these black points there, the gray bands here. Pushes you over that Fermi limit. Okay, so this is actually a relatively sensitive test for the presence of those inverse Compton cascades. Of course, in our picture, there are no inverse Compton cascades. All that energy is going away into plasma instabilities. It's not being re-emitted at GeV energies. Okay? So we're not necessarily stuck with the conclusion that there can't be many at high redshift. Again, this background is just a projection of the luminosity function. Now there's a weight that depends upon both absorption and the spectrum, but we can go ahead and do that sort of thing. Here's where the story stood as of a few years ago. This red line was our favorite. Okay, this is our prediction. There are a few other lines. The first is this green line. This is what you get if you don't include the absorption on the extragalactic background line. So this is unabsorbed extragalactic gamma ray background. If you have inverse Compton cascades, that moves all the energy in this green line down to lower energies. Okay, not too much, right around here, and that's exactly where those tensions that I was talking about before come in. So this green line is what absorption, without absorption. The blue line is what you get if you just remove all the absorbed flux, but you leave in all the sources that Fermi should be able to identify. This is the background. This is stuff that Fermi has not attributed to something else. Okay, so you take the blue line and you remove everything else that Fermi should see, and this red line is what's left over. So that's what we compare this to exactly. One interesting thing about the red line is, we have this typical situation that you hear from crackpots. It fits the data right here, and right after the end of the data, there's a sudden drop-off. There's a feature. There's something very different happens. If we only look a little bit further, then you would see, yeah. And usually the data, this fits fairly well with the power law. All of these things are clearly in line. There's a systematic connection between these. I mean, it's clearly just a power law, so we're just being absurd. It turns out that this feature is robust. We can't get rid of it. This feature is because of absorption on the extragalactic background light. If the background is being produced by these kinds of gamma ray bright blazars, then this feature has to be there. You have no choice. Okay? So what does it look like today? Here's the new data. The old data are the red points. The new data are the blue points. And it falls off exactly the way it's supposed to be. Okay? So we get our absorption feature. Again, the dotted lines and the dashed lines are the same, unabsorbed, including sources Fermi should be able to identify, things that Fermi can't identify, and with absorption. And no inverse Compton cascade. We take that energy and remove it from the system. And no parameters. This really is something that depends upon high redshift. So very close by produces only the very highest end of this, but as you get a higher redshift, you get the shape of this ball that matches. Down below this gray region, there are other things in the universe, and there's certainly plenty of other things that can produce the soft gamma ray background. It's getting to the hard gamma ray background that's hard. So we've just completely ignored this. We've said, okay, you can do that with those FSRQs, that other thing that Fermi sees. You can do that with a little bit of starburst galaxies. There are plenty of other things. We're just going to set those aside. This is the place that's difficult, and that's where we do the job. And it really is a measure of the high redshift features. Okay? So the extragalactic gamma ray background, perfectly consistent with this quasar-like evolution. Okay? But only if the inverse Compton halos are absent. Okay? And that's really sort of interesting, because as a theorist, and as a black hole astrophysicist, it feels good to me to think that one accreting black hole is a lot like another. You turn a dial of accretion rate or something, and you change its character. That these blazars are not somehow intrinsically older or later than other quasars. And so having this kind of unification, is something that appeals to me aesthetically. And as long as we lose the IC, the inverse Compton halos, we keep there. Okay, so why should cosmologists care? If it's not going into inverse Compton cooling, if it's not producing GeV photons, that energy is going somewhere. So where's it going? Following reionization, it's very difficult to get a lot of energy out of photoheating. And the reason is simply that the excess energy produced from an ionizing photon in units of rest mass is really tiny. And if you estimate what the temperature is that goes with this tiny amount of excess energy, it's about 15,000 Kelvin, about the temperature in the IGM. Okay? But if we're talking about emission from black holes, okay, even a small amount, okay, even 0.01% radiant efficiency, okay, you still get large amounts, even a small amount of mass in black holes. We still, with a 10% radiant efficiency, we still get large amounts of energy being radiated by black holes. Okay? And so, if TeV blazar heating, if this TeV photons for blazars are being turned near unity, near 100% efficiency into heat, which is just a range of motions that our plasma spillies end up at, then the typical amount of energy we can get per unit mass is something like 10 to the minus 8. Okay? Which is an order of magnitude higher than the kind of energy you get from photoionization. So this really can be quite significant. As long as this efficiency is order unity. The reason why this is so small is because this efficiency is so small. One photon, the photon crosses the universe 10 times before it photoionizes. Our TeV blazar, or TeV photons, are eaten up within a few hundred megaparsecs. But this heating is very different than what we normally think about. And it's different for a few reasons. The first is the infrared photons that they're pair producing off of are nearly homogeneous. Not exactly, that's something to worry about, but nearly homogeneous. Second is the cosmological mean free path of our gamma rays before they pair produce mean that they wash out the bias associated with galaxy clustering. Right. And the weakness of the instability on the actual density of the IGM means that low density and high density regions are heated roughly similarly. Now, here's a plot of how many blazars, TeV bright blazars, you would expect to see in your night sky as a function of redshift. Okay, that's the number that Fermi sees right around there, exactly what the difference in normalization is. But we would estimate that you should see at least one out to redshift of 5. Okay, so of course, the TeV blazars aren't turning on until about then anyway. Okay? So all of these things combine to give us a heating rate which is nearly volumetrically constant. So the rate of heating doesn't depend on the local density, it depends upon local volume. Same amount of energy density being dumped in each cubic centimeter of the universe. And that means low density regions are going to get particularly hot. Okay? So this is very much different than the other kinds of feedback people talk about. Things like stellar winds or bubbles in clusters, where this is highly localized to regions of high mass. This stuff permeates the universe. It's sort of like a universal time-dependent preheating. And the amounts of energy you can get are enormous. Okay? You can raise the IGM to temperatures, just typical heating rate given by the TeV flux at Earth from various sources on that list, gets you up to a temperature of about 10,000 Kelvin, 100,000 Kelvin if you're at mean density and you integrate over Hubble time. Now, of course, at earlier times, the luminosity density of universe of blazars or AGM is much higher. Okay, so here we are today. Earlier times is much higher. Okay, so in principle, we should be setting the heating rate proportional to this growth as we go back in redshift of luminosity, integrating up and worrying about the thermal state of the universe, worrying about terms like adiabatic expansion, changes in species, and here in this heating term is where you add things like photoheating and our TeV blazar. What does this really look like then? The temperature for a mean-free patch, or a typical patch. The solid lines show for different models of reionization exactly what the temperature looks like. It follows this characteristic adiabatic cooling section for our heated, blazar heated universe, where we add blazar heating to this Q dot term. It jumps up by the magnitude.
Does this change the UV background at all? If you're heating this kind of material to 10 to the 5?
How do you want to change the UV background?
Well, if you're just having material then cooling around 10 to the 5.
It's all iron. If you have a way to directly detect it, we should. Only for
Very, very diffuse Lyman alpha.
how about Lyman alpha absorption? You could do that.
Well, the recombination will produce emission.
Yeah.
Well, if it's uniform or redshift, the uniform background is very hard to detect. I don't
But it's a
think
line. It's a line.
No, it's not a line because it would be under a single redshift, but it comes from all redshift, so it's fills all that. There's
No, it's
no
only a redshift
recommendation.
of 30. Well, not even 20, 10. No, it's 5.
No, it's a feed.
It's 2. Yeah, exactly. But it's going to be the integrated luminosity is not that high.
So I think we thought a bit about different direct detection schemes. And I'm sure we thought about recombination, but I'd have to revisit.
It's going to be really slow.
Yeah.
The density.
No, right. I mean, so this dramatic enhancement at mean density.
But that's a low density.
That's very low. So what does that do? Just to
Let me
give
go
you an
back to
idea.
this and show my ignorance. So you have an enhanced temperature, essentially from redshift 5. That's going to have an impact on the hydrogen abundance. I'm not quite sure why the remark on red tissue is done.
Well, but there's other ways to ionize the neutral hydrogen, which have already been going on, which is the UV radiation coming from the galaxies. It's not
Well,
going to
no, I know, but.
It's not going to affect the ionization.
This is a great question, and if you wait 5 minutes, I'll have a
You're
good
going to
answer.
solve all problems. Okay, that's good.
So just to give you an idea of what it does to the temperature, okay, it's highly density dependent. This is what things look like without the new heating term. The new heating term turns up the low density end, but just the low density end, not the high density end. Okay, So that if I were to put things on the same scale, you know, high densities end at the same place, low density ends at the same. There was a claim a little while back that there was an inverted equation of state, that you needed to have low density gas hotter than high density gas from Lyman alpha measurements. I'll show you some examples of those fits. Here's the slope that is claimed you needed, and that looks a lot like at Z of 2, around what we were getting. Okay? This is just for slightly more or slightly less heat. Okay, so let's actually look at that in detail. So here's a calculation that plugs this heat in and follows the photoionization, follows the ionization state.
So,
of
but
the
this
universe.
is exactly what we were just talking
Yeah, but so yeah, we're not looking at I don't think we looked at the
about.
recombination.
By and large.
We're not looking at we're looking at the absorption lines though.
Ah, this is an absorption.
This is an absorption. Yeah. So this is no blazer heating. We see that low densities are cooler because of adiabatic expansion. Intermediate blazer heating, we see with laser heating, we see low densities are higher. Okay? And what it does is it changes the neutral hydrogen fractions. And so we go from having something like this dotted line, where you have deeper features, to this solid line, where the features are a little bit less pronounced. Now, something we caught a lot of flack for when we first went out and we started talking about this was that we noticed that Lyman alpha calculations were often fudged. You'd compute the ionization state of the universe with one UV background. You'd measure your Lyman alpha optical depth. You'd get the wrong number, and you'd go back and rescale everything, even though it's not really a linear process. And we said, yeah, that's crap. How can you get away with that? Well, it turns out that the UV background is sufficiently poorly constrained that you can sort of do that. We don't have to do that at all. We can just take, recent, well, not so recent anymore, standard UV backgrounds, plug them in, and get the right opacity. So we think that's kind of neat. Not sure if that's significant. But then we can go off and we can look at probability distribution for a given line depth. Depending upon whether or not you fudge that background or you tune the background, we do better at the high transmittance. Exactly the region that's dominated by Lyman alpha in the low density regions.
We tried the reverse experiment where you turn off the UV background altogether.
No.
So which one's the bigger effect?
Oh, well, so we might be able to get that just from these two pictures here. So this is what happens if you take that UV background and you don't allow it to vary. So then if we think, what is the typical scale over which people refudge their UV background? It makes a difference from that to that.
So it's comparable.
It's comparable, but I guess the question I have then is at fixed redshift.
So but you can just do the experiment. You do the calculation, just subtract out all the UV background.
And just look at the ionization state without UV.
So how do you get?
We have not done that.
Normally you use ionization equilibrium, you turn off UV, everything is neutral.
Well, it's at 10,000 degrees and it isn't.
So that's because you UV background. Turns off
No,
all
no,
UV.
No. It's being heated by this other stuff.
So he's getting it ionized just from collisional ionization.
I'm really, well,
Wow.
I guess, I think I still need it to be ionized.
You didn't have
I
that.
understand that. So I'm just asking a question. Run the experiment the other way. You turn off the UV and see what the ionization fraction is just from this heat.
Even though that's not consistent, because we need to have an ionized IgM to have the plasma stability.
Well, once the instability gets going, it'll go, right? So we just assume something started it off. Okay.
I'll think about that. In any case, yeah. So we can do things like look at the probability distribution of line fluxes. You can look at power spectra in the Lyman alpha lines. All of these things tend to look better at these large scales.
So what sort of large-scale homogeneities are induced by this?
What do you mean induced?
Well, it's because you have a different heating source.
You're blowing up the
Very
voltage, for
large
example.
scale associated.
Yeah.
And so
So you
you
blow-
could imagine that you would be using a large-scale modified bias, just like the proximity effect does. So
Yeah.
this would be much more
I don't-
widespread and ubiquitous, and that would call into question the basic assumptions that go into all of this attempt to do cosmological parameters in one
So right now, all we did was take the new heating. Well, this is a good question. I think that the new heating was just inserted in order to get the ionization balance. I don't think, yeah, we haven't run a simulation yet with the new heating term to see dynamically what it does. I can point out to what it does to things like filtering mass, but that doesn't get at the question you're really asking. So my understanding is it's very difficult because the effect is primarily in voids, where resolution is typically not so good. So I remember talking to Christoph about this, and he has plans to do exactly those kinds of simulations. He has some ideas of what he might find, but
He's still using SPA.
I wouldn't want to speak for him. I'm not
Because if you are worried about doing it in low density regions, you want to use it.
Yeah,
Base
I
code.
don't think so. I think he's well, I mean, he's that fits.
So
He can go down the
does
hall.
he have access to?
Oh, yes, yes, I just about everything. Well, in any case, okay, so we can skip line widths and all of that. One thing I just wanted to point out quickly, and I suspect I'm running quite late now, is that there have been some people who've talked about using line widths and column densities as proxies and trying to measure this equation of state resistance directly. I'm a little bit nervous about that because they're not terribly good proxies. And this is what our line width column density scatter plot looked like from the same calculation that the preceding slides came from. And you'll notice that it looks pretty much like this one. And so I think the kind of situation that we have is not at all ruled out by the line with column density line with scatter plots that appear in the literature. However, there's an interesting thing here, is this little turn-up. It's not clear what that turn-up is from. It might be from line fitting algorithm issues. But there is a turn-up if you push down to particularly low densities in our calculation. No blazer heating and blazer heating, this turn-up becomes more common. And that might just be that we're looking at sufficiently low density regions this year. Okay, so that might be a smoking gun, and we'll have to see. Now, I have 3 additional slides that I can run through in 30 seconds each. The first is looking at the impact on the growth of structures, so things like dwarf problems. If you heat the IgM, you make it harder to collapse, and it turns out that you solve at least the void dwarf problems. Okay? The second thing is the dichotomy between centers and clusters. Some clusters have cool cores, some don't. They have a large central entropy. And these come in populations with cool cores and populations without, and there's some deficit between the two, and while there's some discussion about how real that is, this naturally follows if you say that these guys formed early, where the merging time was long in comparison to the cooling time, so cool core stayed a cool core, it merged, cool cores missed each other, energy was never gravitational in the process. To late forming, where because of heating, because of the Blazar heating, so late forming after Blazar heating did something, produced an entropy floor, which made big puffy balls. So when they slam into each other, they core shock, gravitationally reprocess the energy of the merger and the heat in the core. Okay, so if you do that. And lastly, there is a H1 mass function version of the void dwarf problem. Okay, it's just a matter of having too little substructure at low masses, too few things at low masses. And a simple way to solve this is, again, to add some amount of entropy injection. How much? Just about the amount that you get from Blazar heating at just about the time that it should be doing it. So, but these are all, possible consequences. There's some things that we're working on. Like clearly, there's some things we should add, but simple things like looking at the helium forest and asking how sensitive is that to heating. Apparently, that happens later, so apparently we can be quite a bit more sensitive. We're looking at how to do that. Another one is trying to find evidence for those EV gamma rays. I'm not wedded to the idea. Maybe we're all wrong, and that these inverse quantum halos are really there. They should be there for things if there's an intergalactic magnetic field where we don't see the TeV photons. So we're in the process of trying to locate those things. Certainly these temperature density processes, etc. And there are theoretical things. So these are observational. The theoretical things we're trying to do, a better job of plasma physics, looking at bias by having lasers turn on in high density regions earlier, Well, here we go. Simulating gamma galaxy formation in the voids, etc. And so in conclusion, let me just say that plasma physics might be important for cosmology. It might be time to invest in a good plasma physics book. And we'll keep you posted on whether or not we can show this doesn't happen at all. Thank you very much.
We had a lot of questions, but I think we have time for a couple quick ones.
Just to see if I follow in this picture, so the mean field passes at redshift 3 or 4 is only a few tenths of megaparsecs, and the ability to talk about that number roughly. It's fairly short, even compared to the mean quasar separation. And
the mean free path today.
yes, it's a gigaparsec.
About a gigaparsec.
That's right. And redshift 3 goes 1.0 to the 4th, so it was something.
No. So it goes 1.0 to the 4th initially because star formation. But after redshift of 1, it pretty much levels off at 35 physical megaparsecs.
Physical, but maybe 100 moving, which is comparable to the mean separation of two such quasars. The mean quasar density 10 minus 6 megaparsec cubes is about 100 to 1 per 100 megaparsecs. So that's going back to what Dick is saying. It means that this is, all the unity patch here, I would have thought, since the number of any given atom is illuminated by half or the unity or less. Of these. Now, in addition, these to be fairly highly beamed. So there's only a cone that you're really doing this to.
Yeah.
And again, your beaming angle, it seems like it's going to be a relatively smallish number, which is why not all lasers do that. So that means that the flashiness, I would have just multiplying those would be quite substantial, I would have thought, isn't it?
So the beaming angle turns out not to matter. It doesn't matter because we calibrate the total number of objects to the total number C. If you have smaller jets, higher beaming, you have to have more objects to equal the number you see. So we went through some effort. How do you define what the patchiness should be? This line is the number of objects that are producing half of the helium. That's what that line is.
For a given atom in the IGM.
For a random point. And you're right. By Z05, it's trying to get very patchy. But by Z05, I think they would have no heating anyway because they're no engineering. There is some patchiness potentially associated with the fact that you'll have more blazars in the highest density regions turning on for others. And this is something we're looking into. But I don't think it's not expected to be terribly patchy. After all, how many of them do we see today?
NP of 10 means 30% patchiness.
Oh, yeah. Sure.
Well, we had a lot of questions, so I think we can ask Avery more questions over cookies. Avery is only here for about 1 more hour, so if you have questions, ask them too, and let's thank him for